This is VLSI data conversion circuits, lecture 11. In the last class we were discussing how one should choose the input frequency in relation to the sampling rate so that the resulting discrete time output sequence is periodic. The motivation for making the output sequence or the sample sequence periodic is that we will be able to decompose it into a Fourier series which is now discrete time, and then look at the various Fourier series coefficients and identify the coefficients with the harmonics. And towards the end of last class we saw that this Fn by Fs being equal to m by n, where n is the periodicity of the resulting sample sequence and m is an integer, is just a necessary condition, right. It is not sufficient, because if m and n are not chosen within quotes properly, then one can have the situation that several harmonics alias onto the same frequency bin, right. I mean, causing us to wrongly conclude that there are no distortion components, or make erroneous judgments about the frequencies of the distortion components. A case in point being, the last time we said if we chose n to be 2 to the power 10, which is 1024, and m to be 256, the motivation being that we wanted to test the performance of our sample and hold around Fs by 4. Clearly m is an integer and so is n, and the ratio of the two is 1/4. But then we saw that the second harmonic, the fourth, the second, the sixth, the 10th harmonics all alias to Fs by 2, the fourth harmonic, 8th, 12th all alias to DC, and all the odd harmonics alias to the fundamental. So for example, if we had a sample and hold which fundamentally had no even harmonic distortion but had only odd harmonic distortion, which is a very normal thing for a class of circuits to do. For example, you can have a class of circuits where only odd harmonics are produced. Now if you take such a sample and hold and put in a tone at exactly 256 by 1024 times Fs, which is Fs by 4, all the harmonics will alias to the fundamental, and when you look at the spectrum it will look like, wow, my sample and hold does not add any distortion at all, whereas in reality what is happening is that all the odd harmonics are aliasing to the fundamental band, right. So in the time domain, if you look at it, 256 by 1024 is what, 1/4, right, which means that the periodicity of the sequence is how many samples? It is only 4 samples. Even though you express it as 256 by 1024, the real periodicity of the sequence is only 4 samples. So let us say we put in a sinusoid, a clean sinusoid as the input, and let me okay. And our sample and hold is really bad. So when you put in a sinusoid, let us say it is producing a square wave, right, you can't get any more nonlinear than that. So for argument's sake, if we say the nonlinear component of the sample and hold is actually the square wave which is being sampled by an ideal sample and hold, that is the model for the sample and hold that we established, okay. Now if this is sampled, the samples are these, you understand. So the black curve is the pure sinusoidal tone to the sample and hold, the red wave is that which has been distorted, and the samples in magenta, sorry, or the samples in blue represent the values that are obtained after sampling, correct. Of course, we have no access to either the black curve or the red one. We are only trying to discern or reconstruct what the input might be and what the sample and hold is doing to the input by looking at the blue samples, right. And what do we see? The samples that we are seeing are this is some A, this is A, this is 0, this is 0, this is 0. So, we are seeing a sequence 0, A, 0, minus A, 0 and so on, and it does not take a genius to or even a computer to decompose this into a Fourier series. What is the Fourier decomposition of this series, of the sequence? The sequence is 0, A, 0, minus A, 0, A and so on. It is a single sinusoid at what frequency? Right. So, this is simply cos, sine omega n, where omega is 2 pi by 4, correct. So, this is sine pi by 2 times n. So, if you plot the discrete Fourier series coefficients, you will get a big peak. I mean, see, please note that 2 pi corresponds to 1024. So, pi by 2 must correspond to 256. So, at m equal to 256 you will get a spike, and that will be the only spike in the entire spectrum, okay. And then you look at it and what do you conclude? You conclude that, hey, I put in a clean sinusoid, I look at the output spectrum and it appears clean. So, my sample and hold is working just fine, okay. Whereas, we see that what is actually happening is that the sample and hold is doing a terrible job by taking the sinusoid and distorting it and making it look like a square wave, right. In spite of that, by looking at the output spectrum, I am not able to figure out that bad things are happening inside, and the reason for this is that all the odd harmonics are aliasing back onto the same bin as the fundament, right. Okay. Another way of thinking about it is that if the input was chosen in this way, that is to be equal to 256 by 1024 times Fs, right, every time you are pretty much sampling the same 3 values. So, you are every time you sample, you are either sampling around the 0 crossings or at the peak or at the negative peak, right. So, you are not exercising the sample and hold for other values of the input. It is only these 3 sequences, I mean values that you are looking at, right. So, which is why you are missing the action in other parts of the sinusoid, which will happen if the input frequency is chosen wrongly. So, what do you think we can do to fix this problem? Clearly, you must make sure that the harmonics do not alias to either the input or to any other harmonic. Of course, if for example you have a 1024 point record, then how many unique harmonics do you think you can fit in the FFT? So 512 is, I mean, DC, and then the 500 I mean, you know, only up to 512 are unique, right, the rest of it is a mirror image. So and most workable systems, the harmonics will die down beyond about 5 or 6, okay. So in other words, if you take a reasonable record length, then you will have lot more bins than harmonics. So it is easy to make sure that the harmonics, at least the first 5 or 6, you know, do not alias onto either the fundamental or any of the other harmonics, okay. And a simple thing to do is to choose M and N to be relatively prime. As an example, in our case, if you want to characterize the sample and hold at about Fs by 4, the thing to do is to choose, for example, as we did, say 247 by 1024, okay. And if you want at Fs by 2, you should not put in 512 by 1024, okay. Again you will have the same problem. If you put 512 by 1024, you are only looking at, you know, the top maximum and the positive and the negative maximum. So even if this square wave, I mean the sine wave has become a square wave, if you sample only at 2 points, right, you will always be able to fit a sinusoid into the sequence, and therefore will give you totally erroneous, it will give you right results, but that will I mean, you know, it will lead you to erroneously conclude that your sample and hold is perfect. Does it make sense? So for example, if you want to characterize it at Fs by 2, a reasonable choice I suppose would be, say, 503 by 1024, okay, or, you know, choose something else which is relatively prime. Does it make sense? And a caveat, when you run simulations, you know, you must have this in decimal form to the complete precision, right. You should not, do not truncate it after 2 or 3 decimal places thinking the others are do not really matter, okay. I will discuss what happens if you truncate right now, but you should not do it. If you do, you will see weird things happening in the spectrum. Does it make sense? Okay. In practice, when you are making measurements in the lab, right, you need to therefore have Fin and Fs. Fs is usually fixed because you are trying to make a sample and hold which samples at this frequency, and it is your job to produce an Fin which bears some, you know, rational relationship with Fs. So you want to make, in other words, Fin you want to generate Fin such that Fin by Fs is a number of the form m by n, where, you know, n is a power of 2 and m is an integer which is not which is relatively prime with n. The question is, how would you do it? A, you can take one oscillator. Let me take an example. Let us say Fs is 100 megahertz, and let us say Fin is chosen to be Fs times let us say 259 by 1024 times the sampling rate, which will turn out to be some number which is about 25.xyz UV megahertz. Okay, some frequency like this. So, the question is how would you generate, when this is fixed, what do you think you would do for this? Pardon? No, you need to generate a sinusoid with this frequency. That is what it means, right? Pardon? No, do you understand the question? So, you have a sample and hold, it is sampling at Fs, which is 100 megahertz. You need to characterize the sample and hold. So, you want to generate a sine wave at this frequency, all right. So, can you suggest a way of doing this? Can I, for instance, this, I mean, you have seen function generators in your lab, right, where you can have, you turn the knob and then you get whatever frequency you set. So, one way of doing this would be to take a function generator and set its knob to 100 megahertz and take another function generator and set it to 25 point whatever xyz UV megahertz. Do you think this is a good way of doing things?
Use 100 megahertz to upsample by 1024 and downsample by 250 cascade.
No, I do not want a sequence, I want a continuous time sinusoid, you understand.
There are chances that it may tune into 258.
Okay, the one question is, okay, is it possible to find a function generator where you can set the frequency so accurately? So, let us say you can. Do you understand the question? What is the question? What is the question? Can somebody rephrase it in your own words and tell me? What are we trying to solve? What are we trying to do?
We are trying to provide two clock sources to the sample and hold, Fin and Fs, and
I mean, the clock only goes to the Fs.
Yeah.
That's a sampling clock, yes?
yeah, and we want to maintain that m by m relationship between Fin and Fs.
Yes. Okay. All right. So, one, I mean, the first thing that would strike my mind is I need two frequency within course generators, one which generates 100 megahertz, which I will use as a sampling clock, and the other one which reads, which generates 25 point blah 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 megahertz. I will filter it, make sure that it is sufficiently clean, it has to be a single tone, mind you, and plug it into the sample and hold, right. And why am I interested in making the input frequency exactly 25.1 xyz megahertz? So that the sample discrete time sequence is periodic. Okay. Now, any comments on this way of going about things? Do you think it will work or it will not work?
Because the sources are all independent,
Yes.
and I don't think it is practically possible to maintain this exact ratio 259 and 1024 between two independent sources.
Okay. How about if okay, so the comment I got is it's not possible to maintain 259 by 1024 because these are don't look like very friendly numbers. How about if it was 256 by 1024? Do you think you would be able to maintain it?
Actually, it's not the number as such, it can be varying, right? So,
Accuracy of those sources we have
Pardon?
it can be, you can't have a fixed frequency, it can keeps slightly changing it with time or
Which one? I mean both of them or one of them
like
or?
relative to each other,
Okay.
and then we can lose that ratio.
Yeah, so it turns out that if you take, I mean these are nothing but signal sources are nothing but oscillators, isn't it? Okay, and each of these oscillators have different frequencies or time periods, and since they are completely independent, it becomes impossible to be, both of them cannot be in sync, right. It is like saying, okay, my watch and your watch for example are both oscillators with nominally the same, hopefully the same frequency, correct. So I mean one simple thing we can do is we synchronize our watches today, right. If these two are exactly identical, then I come back 40 years later and then it must still be showing the exact same time. I mean clearly that does not happen. Why? Frequency is a function of a whole bunch of things, right, and since the sources of noise affecting his oscillator are very independent and different from those affecting mine, right, the two will drift with respect to each other, you understand. So even if you manage to get a generator which is good enough to be able to specify its frequency to 6 decimal places, right, these two, if Fs and Fin are two independent sources, you will find that even though nominally the ratio is 259 by 1024, they will drift away with time. Just like it's as you all understand, it's utterly impractical to expect that we all set our watches, sync our watches up to something today and expect that we can continue on for 10 days and then all our watches will still show the same time, right, because there are, though they are all nominally identical with respect to the frequency of oscillation, that there are differences, small differences, and then there is noise and so on, and they will all drift off. Okay. So if you do not want these watches to drift off after you come back for 40 years, right, what do you think you can do? Pardon?
Observe for every year.
Every?
Some duration.
And
Correct.
so I mean if you want these independent oscillators, so to speak, to be in sync, you periodically synchronize them with respect to, I mean either a reference which is stable or one with respect to the other. For example, all this relationship is telling you is that Fin by Fs is 259 by 1024, which means that there are 259 cycles of Fin for 1024 cycles of Fs. So a conceptual way of syncing these two independent oscillators is that I will measure the number of cycles of Fin in 1024 cycles of Fs, right. If I get exactly 259, I do not do anything to the input. If the number of cycles are smaller than 259, I know that my input oscillator is running too slowly, I do something to speed it up, okay. And if it is running too fast, if there are more than 259 cycles in 1024 cycles of Fs, I slow down my input oscillator, okay. So I keep monitoring continuously and then tweaking my input oscillator such that at all times 259 cycles of the input occur in exactly 1024 cycles of the sampling clock, okay. This is a feedback system, correct. I am looking at number of cycles here, comparing it with what I want and tweaking the oscillator. This negative feedback system is called a phase lock loop, okay. And so it turns out that if you buy sufficiently good quality signal sources, right, they can be phase locked to each other, right. So that even though you punch 25.xyz megahertz on one and 100 megahertz on the other, because they are being constantly synced with a high quality reference, you will find that this precise frequency relationship is maintained over time. Okay. So, this is what is called synchronous sampling. All right, and only when you have the input source and the clock synced in some way will it make sense to talk about f in by fs is equal to this m by n and all this stuff. Does it make sense? What I want to bring to your attention is you just can't take two arbitrary sources and then even if you are able to set their frequencies to 500 decimal places, you will still not be able to maintain the required ratio because the two oscillators will drift over time. Okay. So, that is one thing. The next thing I would like to bring to your attention is what if the input frequency was slightly off, right. For example, what we said was if f in was 129 by 1024 times fs, what would we see in the spectrum? What is the period of the sequence? 1024 samples, and when we decompose it as a discrete Fourier series, you see a big spike in the 129th bit. All the other bits are supposed to be 0, but in practice they will be 10 orders of magnitude smaller than what you see in the fundamental, in the input bin, correct. Now, if what do you think or what should we expect to happen if this was not 1024 by 129 by 1024 by fs, but let us say 129.01 by 1024 times fs. Okay. So, it is no longer periodic, yes.
But I can also express it as 12,901 by 102400. So,
Correct.
period is like
So, if okay, I agree that if you increase the record length by a factor of 100, then indeed it will get, you will get it at the 12,900 first bin. Okay, but let us say I still am only interested in a 1024 point record, right. Either unknowingly or because of truncation in my, or because I was just careless, somehow the frequency is 129.01 by 1024 times fs. What would you expect to see?
When you take a Fourier transform of a periodic sequence, you get impulses periodic.
Sure.
But if you take Fourier transform of aperiodic signal,
Yes.
then it, all the coefficients you will have non-zero. All
Yes.
coefficients will be non-zero.
Okay. So,
Almost.
great. So, let us take a look and get some intuition about what, first of all let us see what happens by doing the computing the series, and then we figure out why this is happening and see what to do to fix the problem, because this is also a practical scenario where sometimes it turns out that you may not be able to sync the clock source with the input. Okay. I mean, if you are lucky for that to happen, great. Sometimes you just do not have the equipment which will give you a sync signal so that the two can be synced together, and you are stuck with a small difference between the two frequencies. I have just taken an arbitrary difference of 1 part in about 100. Okay, 129.01, the difference is 1 part in fact yeah, it's 1 part in about 12,000, right. Okay. So, it is a very, very small difference. So, we would say, hey, what difference does it make, right, 1 part in 12,000, does it really matter? Okay. So, let us see what happens. All right. So, I have computed the discrete Fourier series coefficients for 3 signals. This in green corresponds to an input tone which is 129 by 1024 times Fs. This corresponds to 129.01 by 1024 times Fs, and this corresponds to, what do you think? How do you figure that out? Yeah, sure. I mean, one thing you can say is that as this gets closer and closer to 129, I mean, this should become closer and closer to the ideal one, but that still does not tell us why they should be at 129.01. It actually turns out that it is 129.001, and it turns out that you can actually infer that from the two curves, right, but I will get to that a little later. You understand? The answer is indeed 129.001 times Fs. Okay. So, clearly one of the things that we see is that the spectrum looks terribly wrong. Okay. Mind you, there are no harmonics in the output. This is just the output is within quotes a pure sinusoid, and you compute the spectrum, and my God, you see that all the bins are full, correct. And what does this lead you to conclude? This is, I mean, you would normally, given all the experience so far, we would say, hey, all the bins are full. I mean, my sample and hold is doing all sorts of crazy things. You understand, right? And this is, mind you, for 129.01. If I made it 129.1, what would you expect? I mean, this thing would probably look like something like this, okay. And couple of things. One, if there was indeed a harmonic which was, say, at this level, okay, we won't be able to discern it at all, because getting masked by these side bands, if you will. You understand, okay. And in this particular numerical experiment, I know that my tone is actually clean, and this is an artifact of the FFT. By the way, the FFT is just a fast way of computing the discrete Fourier series coefficients, okay. So, this is nothing but an FFT plot. So, we know now, because we have run the experiment, that these are nothing but artifacts of the FFT. Right, but if you did not know this, I mean, you would be tempted to conclude that there is something wrong with my system, okay. and it also makes sense that as this frequency becomes closer and closer to 129, it seems logical that this this weird stuff reduces in magnitude. First of all, this effect is what do you think you can call this effect? Some famous structure that this resembles. If somebody draws something like this, what would you say this is? This is the I mean looks like the Eiffel Tower, right? So this is often called the Eiffel Tower effect. Okay. All right. I don't quite remember the spelling. Is it double F or single F? So we need to understand A, why this is happening, B, and what can be done to fix this, right. So first let us get to why this is happening. Yeah, clearly this is happening because the input sequence is not periodic, because this cos of 2 pi 129.01 by 1024 times Fs times n by Fs is this is not periodic. All right. And so when you compute the discrete Fourier series coefficients, what are we inherently doing when we compute, when you take a sequence of length L and compute its discrete Fourier series? I mean, so when we find the discrete Fourier series coefficients of a sequence of length L, what we are doing is the following: we are assuming that this is one period of a periodic signal, right, where the signal is basically copy paste forever, right, of this basic sequence, isn't it? Okay. Now let me just go through quickly revise some basics on Fourier series and Fourier transform. So if you have a finite length sequence of length m, capital M here, all right, the discrete time Fourier transform is defined as what? Sigma x of n e to the minus j omega n going from 0 to m minus 1, simply because the sequence is only m long, correct. Now if you expand this finite length sequence into a discrete Fourier series, where the understanding is that the discrete Fourier series is nothing but a Fourier series representation of a periodic extension of this m point sequence, then what is the expression for the discrete Fourier series? X of n e to the minus j 2 pi by m into, so x of whatever, let me call this k, right, n n ranging from 0 to m minus 1. Okay, they are normalizing constants, do not worry about them for the time being. So, staring at these two expressions, what does one conclude? So, the this is nothing but a sampled version of discrete Fourier series is nothing but sampled version of the discrete time Fourier transform. Does it make sense? Alright, I mean this I am sure you have learnt it in your DSP class. Okay. Now, let us try and understand why, given this, let us try and understand why it makes sense that if we choose the input properly, if we choose the input to be of the form m by n, where m and n are integers, there is only a single spike. I mean we have seen that from other considerations before, but let us try and use the correspondence between the discrete Fourier series and the discrete time Fourier transform to understand this a little better. Okay. So, if you have a sinusoid cos A into n, what is its discrete Fourier transform, discrete time Fourier transform? Pi into delta of omega minus a plus delta of omega plus a, right. Okay. Now, if I please note that this extends all the way from minus infinity to infinity. Now, if I take only a chunk of this lasting m samples, right. So, the original sequence is there all the way from the original sequence is there all the way from minus infinity to infinity, but if I am only interested in a chunk of this sequence lasting m samples, then it is in principle equivalent to taking a signal which is cos a n and multiplying it by a rectangle which lasts from 0 to m minus 1, right. So, you multiply this with 0 and this is m minus 1, all right. So, what do you think would be the discrete time Fourier transform of such a sequence? This is now a finite length sequence, correct. It will be simply the convolution of this Fourier transform, which is a bunch of impulses with the Fourier transform of this signal. And what is the Fourier transform of this signal? It is 1 plus e to the minus j omega all the way up to e to the minus j omega into m minus 1, correct. And can somebody give me an expression for this? It is 1 minus e to the minus j omega into m minus 1 into m, is it? I am sorry, by 1 minus j omega, which is nothing but e to the minus j omega m minus 1 by 2 times sin omega m by 2 divided by sine omega t. Correct? Why does this make physical sense? I mean, of course it comes out of the math, but why does that make sense? That term e to the minus j omega m minus 1 by 2.
Linear phase. Linear phase.
So what? What can you say about this sequence? Is it symmetric? Is it an even function of time or an odd function of time? It is an even function, correct, which means that its delay is if you have a pulse like this, sorry, what is this delay? I mean, simplistically speaking, delay is nothing but the so called center of gravity of the pulse, correct. So if you have an even function of time or even function of n in this case, its delay is 0, right. So but what is the delay of, what is the average delay of this sequence? M minus 1 by 2. So this delay is 0 and this is the average delay is here, correct. So that is why it makes sense that this is e to the minus j omega times. So on the average this sequence is delayed by m minus 1 by 2 samples, that is all. Okay. So we are not really worried about this part because magnitude is 1. What is the magnitude of this character? So this will go to 0 at DC, it must be m, alright, and what happens to this as omega increases? It will decrease and go through zeros and so on, and at what frequencies will it be 0? It will be 0 at omega by 2 must be equal to multiples of pi, correct, must be, let me that pi, 3 pi and so on, sorry, pi, 2 pi, 3 pi and so on, which means that it will be 0 at 2 pi by m, 4 pi by m. So in other words it will be zeros at multiples of 2 pi by m. Okay. Now what we are doing, in other words, what is the discrete time Fourier transform of this whole thing? It is simply the convolution of the spectrum of cos a n, which is simply two delta functions with this sinc, right. So in other words, if I just draw this on only one side, it is simply like moving the sinc to A. So this is the spectrum, the discrete Fourier transform of cos a n times w of n, where w of n is the so called window function. It just selects some period of time, right. This window is, but in particular is of length m, because we are only interested in m samples of cos a n, correct. So this is the discrete Fourier, I mean this is the discrete time Fourier transform of the sequence cos a n times W of n. Now, if you compute the discrete Fourier series of this sequence, what do you think you will get? What did we just discuss? The discrete Fourier series is nothing but a sampled version of the discrete time Fourier transform. So, and sampled it at what frequencies? Multiples of 2 pi by m, correct. So, if this a happened to be a multiple of 2 pi by m in the first place, correct. So, let us say this was k into 2 pi by m, then when you sample this discrete time Fourier transform, your samples will lie exactly here. Is this clear? Which is why when you look at the discrete Fourier series coefficients, you will see just one spike and all the others being 0, right. This is a somewhat long winded explanation of why, if you take a periodic sinusoid in the discrete time domain and compare its discrete Fourier series coefficients, you will only find one spike, okay. But the reason for going into this seemingly long winded explanation is to get intuition as to what will happen when this a, right, which is the frequency of this cos a n, what happens when a is not a multiple of 2 pi by m? What do you think will happen? So, we are basically, if a is not a multiple of 2 pi by m, then what will happen is that the samples will now be all slightly off. So, we will perhaps say that was a. So, we are now sampling here, correct, and therefore, when you plot the discrete Fourier series coefficients, you will get something like this, right. Whereas, if the frequency was exactly, if a was exactly a multiple of 2 pi by m, correct, you would get only a single spike and nothing else. Whereas, if that is not true, you will get something like this, because you are not sampling the discrete time Fourier transform at the nulls, okay. And clearly the spectrum of W of n has a bearing on how rapidly this Eiffel Tower decays. Is this clear? Okay. So, this phenomenon where a is not exactly a multiple of 2 pi by m is often called input frequency not residing on a bin. All right. And this phenomenon where clearly now the other bins are not 0, and this is called leakage in the FFT. Does it make sense? Okay. So, we will continue with, we will get some more time domain intuition into what this means, okay, and that will give us an idea of what to do to fix the problem. We do that the next time. Thank you.